Welcome to the introduction of the course Simulation and Computer Graphics. My name is Matthias Teschner. I'm a faculty member in the Computer Science Department at the University of Freiburg, and I'm responsible for research and teaching in computer graphics. Before we start with the actual introduction to this course, I'd like to give an overview of our teaching activities. First of all, we offer a general introduction to computer graphics. This introduction is part of the key course Image Processing and Computer Graphics, where the introduction to graphics is combined with an introduction to image processing. In the graphics part of this course, we talk about selected aspects of modeling, rendering, and simulation, with a main focus on rendering. In addition to the key course, we offer two specialization courses. One specialization course is concerned with rendering, the other one focuses on simulation. Now here in the simulation course, we are concerned with concepts to simulate deformable objects, rigid solids or fluids, and here we mainly look into particle-based approaches. In the advanced computer graphics course, we look into so-called global illumination approaches, for instance virtuosity or stochastic ray tracing. In order to realize photorealistic images, it's important to capture the entire light transport in a scene. So surfaces are not only illuminated by light sources, but surfaces also illuminate each other. And such effects are captured by global illumination approaches such as virtuosity or stochastic ray tracing. And in the advanced graphics course, we focus on such global illumination approaches. In addition to these courses, we also offer seminars, an animation seminar and a rendering seminar, and we also offer all types of projects and theses. We offer bachelor projects, master projects, lab courses, bachelor and master theses. And in terms of the projects and theses, we distinguish two tracks, a simulation track and a rendering track. When interested in graphics at the University of Freiburg, you can either focus on simulation or on rendering. So if you are more interested in simulation, you can start with the simulation course in the winter term. In the following summer term, you could attend the key course on graphics. The key course and the simulation course are rather independent. The key course has a strong focus on rendering, so it's not necessarily a prerequisite for the simulation course. In the summer term, you could also do your lab course or attend the simulation seminar. Then in the following semester, you could continue with the master project and then finally write your master thesis. In the rendering track, you could start with the key course in the summer term, and then you could attend the advanced rendering course in the following winter term. In parallel, you could also participate in a lab course and in a master project. Of course, you could also attend the rendering and the simulation seminars. Again, the track would be completed with a master thesis. I find it particularly important to thoroughly plan the projects and the thesis. On one hand, one could do the lab course, the master project and the master thesis in different areas of computer science. The question, however, is whether this makes sense. I would actually argue that it's better to do the lab course, the master project and the master thesis in the same area. In this case, the master thesis can be built upon the results of previous projects. This is illustrated here for both tracks. In the simulation track, for instance, one could implement a simple fluid solver in the lab course. This simple fluid solver could be extended or improved in the master project. For instance, the data structures for the neighbor search could be improved, or the pressure computation could be improved by incorporating a so-called PPE solver, where PPE stands for pressure-Poisson equation. Based on the results of the master project, it would be possible to write a master thesis that addresses very interesting, challenging and relevant aspects in fluid simulation. So in the master thesis, it would be possible to focus on a research-oriented topic. The same holds for the rendering track. In the lab course, you could start with a simple ray tracer. In the master project, this ray tracer could be extended to a sophisticated stochastic ray tracer that employs Monte Carlo integration, and the data structures for the ray traversal could be improved. Then the outcome of such a project can be the basis for a highly interesting rendering topic that is covered in the master thesis. That's it about our teaching activities in the graphics group. And now here we have the outline of the introduction to the simulation course. I start with the motivation of the course topics. I will give you an idea of the research areas that we incorporate in this course, and I will discuss the relevance of the topics that we cover in the course. In particular, I will discuss various application areas where our simulations are being used. In the second part of this presentation, I'm gonna introduce the actual topics that we cover in the course, and at the end, I discuss some organizational aspects. So first, we start with some motivation. Research in computer graphics addresses various topics. So the most prominent topic is certainly rendering, the generation or synthesis of images, but graphics is also concerned with topics that are related to image generation. And here two prominent graphics areas are modeling and simulation. On the right-hand side of this slide, you can see images that illustrate these three areas: modeling, simulation, and rendering. You can see a surface that is represented with a set of vertices and surface patches. You can see the simulation of a fluid, and you can see the final photorealistic rendering of the scene. Now in this course, we focus on simulation aspects. The goal of the course is to provide you with insights how to simulate the dynamic behavior of moving objects. In particular, we will look at rigid bodies, elastic solids, and fluids. Now, this video is a nice illustration of some aspects that we address in the course. Throughout the course, we focus on particle-based simulations. So, for instance, in this video, all objects and all materials are represented with sets of particles. The entire fluid body is sampled with particles. The canyon consists of particles, and also the creatures are represented with particles. Now, the main goal in a particle simulation is actually the computation of the movement of all particles over time. So we reconstruct positions and velocities of all particles over time. Therefore, we consider forces or accelerations at particles. These forces change the velocities of the particles, and the velocity of a particle changes its position. Now we constantly compute forces at particles so that we can constantly update positions and velocities at particles, and then finally we end up with a simulation result as shown in the video. In terms of forces, we compute forces that depend on the respective material of a particle. So for instance, at fluid particles, we compute a force that preserves the volume of a fluid particle. With regards to rendering, we rarely render the simulated particles, but instead we render, for instance, reconstructed surfaces. So the fluid volume is sampled and simulated with volumetric particles, but for visualization purposes we reconstruct the interface between fluid and air, and we represent this interface either explicitly with a triangulated mesh or in an implicit way. These representations of the interface are finally visualized. In this course, we touch various research areas and we combine aspects from these areas. Our main focus are efficient and reliable components for the simulation of the dynamic behavior of fluids and solids. And in this context, we do not just focus on individual isolated aspects, but instead we are interested in solutions that allow a versatile interplay of different simulation components. In the video that I've shown on the previous slide, we had different fluids and solids, and all the objects were interacting with each other. So our focus is on unified solutions that allow to simulate a variety of materials in a versatile way. So in this course, we discuss computer science aspects in the context of physically based simulation. Among other topics, we will have a focus on algorithms and data structures to realize simulations. In addition to this, we also briefly cover some aspects from continuum mechanics and also from numerics. Here we will look into the derivation of forces from strain and stress definitions, and we will look into numerical integration schemes and linear solvers. All these topics, however, will be discussed from a computer science perspective. Simulation research in computer graphics is often referred to as physically based simulation. Sometimes it's also called animation, but typically animation refers to scripted, user-specified motion sequences, in contrast to simulations where governing equations and realistic forces are used to obtain physically based results. What we do is also related to scientific computing. In particular, we investigate numerical integration schemes, realizations of linear solvers, and the respective data structures, algorithms, and also their parallelizations. Dependent on the actual application area, physically based simulation is sometimes also referred to as real-time physics. In the context of games, for instance, or in medical simulators for educational purposes, there's a strong focus on speed and interactivity, which is expressed in the term real-time physics. On the other hand, our research is also used for large, highly detailed scenarios with a particular focus on accuracy, for instance in computer-aided engineering. Here our research is typically referred to as high-performance computing. Now in the following, I'd like to showcase some areas where our research results are being used. The most obvious and prominent area is certainly visual effects for movies or commercials. Here in this video, you see a swimming ship that is hit by highly viscous objects. The scenario should emphasize the fact that we are not only interested in just simulating single objects, but instead we are interested in the interplay of different simulation components. The ship, the fluid, and the viscous objects, they all interact with each other in a way that is governed by physical laws. We are also interested in versatility and flexibility. The geometry of the ship, for instance, is highly complex, and actually our simulation methods allow to process arbitrary geometries in such a scenario, no matter how detailed it would be. This is basically due to the fact that all objects are uniformly represented with particles. We just compute different forces at the particles dependent on the respective material that they represent. The second important application area is computer-aided engineering, and here our group has a focus on simulations that are used in the context of automotive design. The simulation components that have been used to generate the video on this slide are exactly the same methods that have been used in the visual effects scenario in the previous slide. So the car is represented with particles, the surrounding air is sampled with particles, and here we see the simulated airflow around the car. In contrast to the visual effects scenario, this simulation consists of a larger number of particles, and the visualization of the simulation result differs. Instead of visualizing positions of surfaces as in the previous video, we here visualize velocities within a volume. The colors blue, green, yellow, and red indicate different velocities, and the velocity field is shown for some user-defined planes that intersect the volumetric simulation domain. Our research in physically based simulation and its applicability to computer-aided engineering have led to a spin-off. The name of the spin-off is 52 Technology, and the company has a focus on fluid simulation in the context of automotive applications. The software that 52 develops is named Prion Lab, and its success is mainly based on three aspects, which are efficiency, usability, and reliability. The software combines simulation accuracy with speed, and it also comprises versatile pre- and post-processing components for advanced analysis and visualizations. The video on the right-hand side shows an example of a Prion Lab simulation. As in all previous videos, the simulated components are all represented with particles, and in this specific scenario, a user is interested in analyzing and optimizing the oil lubrication inside the gearbox. Another popular application area for physically based simulations is computational medicine. For instance, simulations can be used for the preoperative planning of surgical procedures. This is indicated here in the images for a craniomaxillofacial procedure. The goal is to estimate soft tissue changes due to the realignment of the underlying bone structure. So the surgeon adapts the position and the orientation of the mandible in this case, and then simulation is employed to compute the respective soft tissue changes so that the surgeon can assess how a patient would look like after the procedure. A second application would be the interactive simulation of medical procedures for educational and training purposes. In the image we see a hysteroscopy scenario with some polyps, and here the goal would be to remove these polyps without damaging the uterus that can be seen in the background. The last example would be intraoperative support for surgeons. Here the general idea is to use simulations in order to update preoperative data during a surgery to keep it consistent with the changes that a surgeon introduces to the patient. So prior to the surgery, a patient is scanned and this data is typically taken by the surgeon for navigation purposes during the surgery. The problem is that the surgeon interacts with the patient, so the preoperative data is typically no longer valid during the surgical procedure. That's why simulation can help to update the data intraoperatively, and this idea is indicated here in case of an orbital reconstruction. Now here we see the interactive hysteroscopy simulation in action. We see the inside of a uterus and some polyps. You can see that a user can interact with these polyps and they deform and they interact with each other. And the structure in the background is also simulated as an elastic solid. Now the goal of this tool is to train a user so that the user is able to remove the polyps from the wall in the background without damaging the wall. As always, the simulated objects are represented with particles. And in this case, each particle has the shape of a tetrahedron. If a tetrahedron deforms, then we compute forces that try to preserve the original shape and size of the tetrahedron. You can see that we use different representations of the scene for different purposes. For the visualization, we use triangulated surfaces, which are attached to the volumetric tetrahedral representation that we use in the simulation. Another application area for real-time physics are games. In nowadays games, we see lots of simulations. The simulation of rigid solids is highly popular, but we also see simple particle simulations for fire, smoke, dust or snow. And here on this slide I've listed some companies and some of their activities in the context of physically based simulations, or more specifically in real-time physics. In games or in other interactive simulation settings, we typically have a specific focus on robustness and versatility. Different animation aspects are supposed to work hand in hand, and all simulation aspects should support a smooth realization. So adequate object representations are important to realize versatile and robust simulations. And also the methods for the computation of the dynamics in a scene and for the constraints should be robust and versatile. These ideas are illustrated in the video. We see a real-time simulation where a user can interact with all objects. The objects are geometrically complex, they are deformable and they interact with each other. And here, in addition to speed, robustness is particularly important. We can, for instance, see that the user turns on and off the collision handling among the cows and everything stays stable. In such an interactive simulation, accuracy is less important, but instead robustness has the highest priority. Typically, interactive simulations in simulators or in games should be stable under all circumstances. That's it about the general introduction to the ideas and concepts behind this course. Now in the following I will introduce the actual topics that we cover in the course. So here we have an overview of the topics that we address. I've already discussed that the simulated objects that we consider are always represented with a set of particles. Therefore we first look into the question how to compute the trajectories of particles. We assume that we know how to compute the forces at a particle, and based on the known forces, we will see how to update positions and velocities of particles over time. In the following, we will see how to compute the forces at the particles. The forces depend on the material that we consider, and in the course we start with elastic solids. If an elastic object is sheared or compressed, then we induce forces that try to preserve the original size and shape of the elastic solid. Next, we look into fluids, and we will see that the force computation for fluid particles is not too different from the force computation at deformable particles. We compute forces that preserve the volume of fluid particles, but in contrast to deformable particles, we do not compute shear forces. The next topic would be rigid bodies. Rigid objects can also be represented with a set of particles, But we will see that in case of rigid bodies, we do not apply the respective forces to the individual particles, but instead we accumulate the forces and apply the resulting force to the entire rigid body. Another important difference to fluid or deformable particles is the fact that we consider the orientation of a rigid body in a simulation. For fluid and deformable particles, we typically do not have a notion of an orientation, but for a rigid body, we have the notion of an orientation. And therefore, rigid body simulations do not only compute the position of a body over time, but also the orientation of a body over time. Finally, in the last part of the course, we look into spatial data structures that can be used to detect collisions between objects. Here we will look into bounding volume hierarchies and space subdivision techniques. So first we start with the computation of the motion of particles. In 3D simulations, particles are small volumes that represent a part of a solid or a fluid. So the entire body of a fluid or a solid is represented with a set of particles as indicated in the illustrations. Here we assume that we have a fluid, but this could also be an elastic or rigid solid instead. Now the fluid body is subdivided into small volumes, and each of these small volumes is referred to as particle. Now each particle is characterized by some quantities. It has some representative position, which can be some sort of center of the small volume, and it has a velocity v. As it has some volume and the represented material has some density, we also get a mass m for a particle. And finally, we can compute a force F at a particle. In the beginning, we assume that we know how to compute this force, so the force is given. The problem that we try to solve is the computation of positions x of time t and velocities v of time t, given the force F of t. When we can compute the positions and velocities of all particles over time, then we have our simulation result. In order to do so, we consider two governing differential equations for the particle motion, one for the velocity and one for the position. So the first equation states that the force acting at a particle corresponds to the time rate of change of the linear momentum, which is mass times velocity. And the second equation states that the velocity is equal to the time rate of change of the position. Now these two equations are numerically integrated in order to reconstruct positions x over time t and velocities v over time t. And here we will look into various numerical integration schemes that can be used to reconstruct particle trajectories. After the introduction to the general motion of particles, we look into different ways to compute forces at the particles to capture the dynamic behavior of different types of material. And here we start with deformable solids. In the images you can see volumetric deformable objects that are represented with particles. Here in this case the particles are tetrahedra. In the image on the right hand side you can see a surface representation of the objects that would be used for visualization purposes. So the tetrahedral particles are used in the simulation while the triangulated surfaces would be visualized. Now, how do we compute forces for deformable tetrahedra? First of all, we define what we consider to be a deformation. For instance, we can say that if a tetrahedron is compressed or if it's sheared, then we have a deformation for which we would like to compute forces that counteract that deformation. In order to estimate whether a tetrahedron is deformed according to our definition, we would process the positions or displacements of the corners of a tetrahedron, and we would store the computed value in a quantity that is called strain. From strain, we compute stress, which basically depends on the stiffness of a material. If you have a soft material, strain causes less stress. If you have a stiff material, then the same strain causes larger stress. And then from strain and stress, we can compute the strain energy, and finally we derive forces that try to minimize the strain energy. So if a tetrahedron is undeformed, we have no strain, no stress, zero strain energy, and no forces would be applied. If the tetrahedron is deformed, we have some strain and stress, some positive strain energy, and we would get forces that try to accelerate the corners of a tetrahedron such that the strain energy is reduced. The concept for the force computation that I've outlined on the previous slide is actually very versatile and can be used for a large variety of materials. Here in this video we see an example of an interactive simulation where we define deformations in 3 different ways and where we combine the respective forces in different ways. The cube that we see consists of tetrahedra, and for each tetrahedron we define deformations in 3 ways. We can say that distance changes between adjacent corner points of a tetrahedron should be considered as a deformation, or we can say that the volume change of a tetrahedron is a deformation, or we can say that the desired area of one of the surface triangles of a tetrahedron should be 0. So if the area is not equal to 0, we consider this face as deformed and compute a force to minimize the area. Now the 3 resulting forces can be combined in different ways. So for instance, if we use distance and volume preserving forces, we have a deformable object. If we add forces that try to minimize the surface of the cube, then the shape of the cube changes. And if we just preserve the volume of the cube, but not distances between adjacent points in the cube, then we get something that looks like a fluid. So the concept from the previous slide is very powerful and versatile in terms of deriving particle forces for different types of material. And in particular, the concept is also used to derive forces at fluid particles. So the next topic would be fluids. As always, the fluid body is subdivided into small volumes or particles. Then we compute forces at the fluid particles. These forces are used to update the velocities of the particles, and the velocities update the particle positions. Now in the context of fluid simulation, the implementation of the whole simulation step is often referred to as fluid solver. And we often say that the main goal of a fluid solver is the computation of the velocity field over time, where the term velocity field refers to the set of all velocities of all particles. Then we also typically say that the velocity of a particle is used to advect the particle. So in our case, fluid particles are advected with their velocity. This sounds trivial and obvious, but is actually not the case for all types of fluid solvers. Particles or samples are only advected in so-called Lagrangian approaches. In Eulerian approaches, they are typically static and have a fixed position. In our research, we have a focus on Lagrangian concepts where we advect the particles, so this will also be the focus in this course. However, if we have time, I will also introduce the concept behind fluid solvers that do not advect the sample volumes. Finally, the forces at fluid particles are computed according to the stated governing equation, which is referred to as Navier-Stokes equation. We see that this is a differential equation that governs the particle velocity. The equation states that the time rate of change of the velocity of a particle is equal to 3 acceleration terms. I do not go into the details here, but each term accounts for some property. So the first term, that is proportional to the negative gradient of the pressure P of a fluid particle, accounts for incompressibility. If a particle is compressed, we get positive pressure at a particle, and if we have particles with different compression levels, then we accelerate a particle from high pressure or compression to low pressure in order to minimize its compression. Rho in this acceleration term is the density of a fluid particle, which can be computed from the mass and the volume of a particle. The second acceleration term accounts for viscous forces. Nu is a parameter that describes the viscosity of a material, and the respective force tries to accelerate a particle such that the difference between the particle velocity and the average velocity of all surrounding particles gets minimized. This can be interpreted as friction in case of adjacent particles that move with different velocities. Finally, the last acceleration is typically just gravity. But here we could also incorporate other types of forces. The stated equation contains 3 types of fluid forces, but one can easily add more forces if appropriate. So for instance, surface tension forces could be added if required. The two images on the right-hand side illustrate the typical setup that we consider. The top image indicates the particle representation of the fluid and of the objects that float in the fluid. The other image shows a typical visualization where we show the interface between fluid and air instead of the individual particles. Please also keep in mind that the particles in the top image are rendered as spheres. Also, they are not actually spheres. In a fluid, we rarely know the shape of the individual volumetric elements, and the shape also does not matter in the force computation. As we do not know the shape, and it also does not make much sense to reconstruct the actual shape of a particle, people typically visualize spheres when they show particles. But again, fluid particles are not spherical. The unknown shape of the fluid particles is illustrated here in this image on the right-hand side, where we have a fluid body that is subdivided into particles. Here on this slide, I'd like to discuss the question how to compute the forces from the Navier-Stokes equation. We have seen that we need to estimate the gradient of the pressure field at a particle, or we need to be able to compute the Laplacian of the velocity field at a particle for the viscosity force. In order to compute the particle forces, so-called discretization schemes are employed. And in terms of fluid forces, we often use a concept that is called smoothed particle hydrodynamics, SPH. The idea of such a discretization concept is to use information at a particle and at adjacent particles to approximately compute the spatial derivatives that are required in a force computation, which is typically the gradient or the Laplacian. So generally, forces or accelerations or velocity changes at a particle xi are computed as a sum over adjacent particles xj. In the illustration, we have our particle xi, and all particles within a certain distance within the black circle are considered as adjacent or as neighbors. Now, for the computation of the acceleration terms at particle xi, we use some quantities that are available at the particle itself and also at all adjacent particles. An example is given here for the computation of the pressure acceleration with SPH. On the left-hand side, we see the acceleration term from the Navier-Stokes equation, and on the right-hand side, we see its SPH approximation with a sum over adjacent particles. M is the mass of a particle, P is the pressure at a particle that is computed from the compression of a particle, Rho is the particle density, and W is a so-called kernel function that governs the contribution of each particle to the final sum. The details are not too important here, but the good news is that the forces or accelerations at fluid particles are always computed as sums over adjacent neighboring particles. Now, there are various challenges that we face in fluid simulation. Two of these challenges that are particularly interesting from a computer science perspective are discussed here on this slide. First of all, the neighbor search. On the previous slide, we have seen that the force computation at a particle requires the neighboring particles. So for each particle, we need to find adjacent particles within a certain distance. Now, the problem is that we typically have large numbers of particles, and we also have the problem that the spatial relations between fluid particles change over time. This means that the particle neighbors have to be recomputed for each single simulation step. And again, generally we have many particles and also many simulation steps. In order to accelerate the neighbor search, we use spatial data structures that typically base on space subdivision or bounding volume hierarchies. Now in the course, I will discuss various implementation aspects in the context of space subdivision. A second interesting and challenging aspect is the pressure computation. The pressure value at a particle characterizes its compression level, and the gradient of the pressure field is used to compute forces that account for the incompressibility of the fluid. Now, there exist simple and fast approaches to compute the pressure, but there also exist more involved concepts. The motivation for using expensive concepts for the pressure computation is actually the potential reduction of simulation steps to get an entire simulation. So one step might be expensive, but we need less steps to get our result. That's why we often prefer to solve a linear system in order to compute the pressure field in a global way. The equation that we consider at each particle is stated here, and this equation is referred to as pressure-Poisson equation. If we consider this equation at all particles, then we get a linear system with unknown pressure values at all particles. Now in this course I will discuss simple ways to compute the pressure, but I will also show how to solve the pressure-Poisson equation. And I will discuss specific matrix-free implementations of such solvers, which are highly relevant when it comes to parallel implementations on one computer or on a cluster. Now here we have another example video that shows what we can achieve with particle-based SPH simulations. And once more you can see the focus of our research and also of this course. We are interested in complex, highly detailed simulations. In terms of the fluid, we are typically interested in so-called free surface simulations, where we have an interface between fluid and air, and we are interested in versatile effects. Here, for instance, we have geometrically complex ships that are two-way coupled with the fluid. This means the influence of the ship on the fluid and the effect of the fluid on the ship both are reflected in the simulation. Here in this image we see a visualization of the particle representation of the scenario from the previous slide. You can see that everything is sampled with particles. The cubes and the ship are sampled with rigid particles, and the entire fluid volume is sampled with fluid particles. All these particles are advected with their velocities, and the velocity changes at the particles over time are computed with forces for the respective material. And if particles from different materials are close to each other, we compute forces that handle the contact. Please note that the color of the fluid particles encodes the particle velocity. Blue particles are slow, white particles are fast. The next video I'd like to show in order to emphasize the fact that we have a focus on efficient realizations of the simulations. Nowadays we can simulate hundreds of millions and even 1 billion of fluid particles on one computer with 256 GB of memory. This is of course much memory, but it's not a cluster. So nowadays, quite complex simulation scenarios with larger particle numbers and large numbers of simulation steps can be computed on standard hardware using state-of-the-art simulation concepts that are being developed in the graphics community. With this last fluid video, I'd like to show that our work also addresses artificial visual effects. So here in this approach we can solidify parts of a fluid and we can melt rigid objects back to a fluid. The realization of such effects is actually not too difficult if you have a state-of-the-art SPH fluid solver. The idea is just to change the force computation at particles. If we solidify a particle, we basically stop the computation of fluid forces at a particle, and if we melt a particle, then we start the computation of fluid forces again. Another aspect is the fact that you can incorporate arbitrary forces or velocity changes or position updates to any particle, which means particles do not only move according to the fluid forces, but also with respect to some user-specified constraints. That's it about the introduction to fluids, and now the next type of objects that I'd like to discuss are rigid bodies. Similar to deformable objects and fluids, rigid bodies are also represented with a set of particles as indicated in the illustration on the right-hand side. The green dots indicate some representative position of small volumes or particles, and the yellow arrows indicate velocities. Now, one important difference to elastic solids and fluids is actually the fact that the particles in a rigid body do not move relative to each other. We can think of these particles as being connected by stiff bars or by springs with infinite stiffness. That's why it does not make sense to compute the trajectories of the individual particles, but instead it's more appropriate to consider one representative position of the rigid body and the orientation of the rigid body. We still compute forces at the particles, but in a rigid body solver we accumulate these forces to update the position and the orientation of the entire rigid body. So forces change the linear and the so-called angular velocity of a rigid body. Finally, the particle positions are updated from the position and the orientation of the entire rigid body. At first, it looks like we do not need the particles at all. However, in terms of contact handling between rigid bodies, and also when we have combined simulations of rigid objects with a fluid, then the particle representation is at least useful for the contact handling. In terms of the involved concepts, rigid bodies differ from particles. Particles have a mass and a position, but typically no notion of an orientation. In contrast, rigid bodies do not only have a mass, but they are also characterized by a mass distribution inside their volume, which is relevant in a rigid body simulation. Also, they have an orientation, and a rigid body simulation computes the orientation of a rigid body over time. And therefore, quantities such as angular velocity and torque are considered in the simulation. When we talk about rigid bodies, I will introduce and discuss these terms and also show how to use them in a rigid body solver. Here we have the list of topics once again. I've already talked about the reconstruction of particle trajectories, and I've discussed different types of material that can be simulated with particle-based approaches, in particular deformable solids, fluids, and rigid bodies. Now, the last larger topic of the course are collision detection and contact handling. Collision detection aims at detecting interferences of the representations of objects. If we have two tetrahedral meshes, then we would like to detect whether one tetrahedron of one object intersects with one tetrahedron of the other object. Such a task can be time-consuming, and a simplistic implementation where we would test each primitive of one object with each primitive of the other object would be of quadratic complexity in terms of the number of primitives. In order to accelerate collision detection tests, spatial data structures are being used, in particular bounding volume hierarchies, space subdivision schemes, or distance fields. The concepts behind the data structures are typically simple, but for the realization of the data structures, there often exist various options with significant differences. For instance, space subdivision can be implemented based on hashing or based on sorting. Now, in this course, I will discuss some of these options. In the illustration, we see one example where collision detection plays an important role. We have the model of a skull, and this model consists of various parts. Now, if we move one part, we need an efficient solution to detect whether parts overlap or not. Here in this illustration, overlapping parts are colored in red. When we have detected a collision, then we need to handle it, and this process is referred to as collision handling or contact handling. When objects collide, we can resolve the contact in different ways, but very often we just compute contact forces. Alternatively, people also compute velocity changes for the involved primitives without having an explicit notion of the respective contact forces. Contact handling can be more or less challenging. For instance, if two elastic volumetric objects collide in a way such they bounce off each other, then the processing is typically rather less challenging. In contrast, if we have so-called resting contact, where objects are in contact but do not move relative to each other, then the contact forces have to be computed very accurately in order to keep the contact stable. It is also more difficult to compute contact forces for 2D cloth simulations compared to volumetric objects. And also self-collisions are more challenging to handle than collisions between different objects. That's it about the introduction to the topics that will be covered in the course. We have seen that the course focuses on the simulation of objects that are represented with particles. We will look into deformable objects, fluids, and rigid bodies. We will see how to derive and compute the particle forces for the different material types, and we will see how to update particle velocities and positions based on these forces. Finally, we will discuss concepts for the detection and the handling of collisions. Throughout the course, we will always look at the simulation topics from a computer science perspective. So there will be a focus on how to efficiently realize or implement the discussed topics. Now, with the last two slides, I briefly discuss organizational aspects. First of all, we see the list of topics that I will cover in the course. In terms of the particle motion, we will look into ordinary differential equations, ODEs, and we will look into schemes to numerically integrate these equations. These schemes provide us with a way to compute positions and velocities of particles over time, given some known force at a particle. Then we talk about deformable solids. Here we focus on a concept from continuum mechanics that allows us to derive forces from user-specified deformations. This concept employs energy minimization, and we will also look into one variant of the so-called finite element method, FEM, to compute forces for elastic solids. Next, we discuss fluids. Here we talk about the Navier-Stokes equation that contains the forces that we compute at fluid particles. And here we will look into so-called discretization schemes, namely SPH, to approximately compute the force terms from the Navier-Stokes equation with simple sums over adjacent particles. As our final material, we look into the simulation of rigid bodies, and after that I will present some spatial data structures that are being used to detect collisions. In addition to the lectures, there will also be exercises. These exercises are not mandatory and also not relevant for the exam. However, if you are interested in the topic and if you think about doing a project or a thesis in the context of physically based simulation, then it is of course recommended to do some of the exercises. And at the end of the course, there will be a written exam. The questions in the exam are entirely based on the slide sets and on the lecture recordings. Please also note that parts of the course are not relevant for the exam. At the end of the course, I will summarize the relevant material, and I will also explicitly state which material will not be addressed in the exam. In terms of additional literature for the course, I'm actually hesitant to make any recommendations. What makes this course special is the coverage of topics from a variety of areas. There exist numerous books on continuum mechanics, differential equations, finite elements, fluid mechanics, smooth particle hydrodynamics, linear solvers, or spatial data structures, but I'm not aware of a book that covers the specific combination of topics that are discussed in this course. Feel free to contact me if you are interested in book recommendations for the respective topics, but in terms of the exam, only the slide sets are relevant. This is actually also the reason why the expositions in the slide sets are typically rather detailed and hopefully self-contained. That's it about the introduction to the course Simulation and Computer Graphics. Thanks for your attention.